All right. Thank you, Nick. All right, so I'm very excited to see everyone here. Some new faces, some of those were already there last year, so this is great. We'll start off the first session with Lorenzo Carnevale. You can come here. Yeah. There you go. And Lorenzo is going to talk to us about some climate change-related issues and how federated learning and drones can help solve those. So very excited about this. Thank you.
Thank you to the Wallflower team, and thank you, Nick. Good morning, everybody. My name is Lorenzo Carnevale. I'm assistant professor at the University of Messina and part of the Future Computing Research Laboratory, where I operate at the cross between distributed system and artificial intelligence. The lab participates in European project, and the talk of today is related to the TEMA project, where we work on natural disaster management, and we have the opportunity to talk with stakeholders and first responders, mostly in fire and flood management. In this case, there are a couple of limitations because first responder often involve a fleet of drones, but these drones are used only for data source, while the drones today are able to make computation because the power is growing day by day. The computation and the communication is often centralized in a standard legacy cloud solution, and there are issues related with the latency when we talk about these scenarios because they have urgent scenarios, and the lack of privacy when we migrate sensitive data. So we see a clear opportunity to move the decision-making computation to the fleet of drones. So we set up the problem as a cloud edge solution where we can run artificial intelligence task, and we give also the opportunity to models to be fine-tuned on the fly, while the drone can fly using federated learning. And so the drone that are the mobile nodes that are deployed in large geographical regions needs a structure like a hierarchical federated learning, because these are organized in multiple levels of aggregations, in multiple servers, edge and cloud servers, and they are forming clusters. So we created a new algorithm, is a novel drone hierarchical federated learning, where we take care of the dynamicity of doing clustering, and we try to optimize according to the need of the drones. So take care of the accuracy, but minimizing energy, training time, and the number of communication. So this is the structure where from the top we have the drones. They train for K1 epoch. They create a cluster with the local edge server that aggregates K2 times, so these are the rounds. And there are multiple of these clusters that every K2 times can have a second aggregation on a cloud base, so in the global server. So we set up the test using MNized in non-ED way, convolutional neural network, and the federated learning configuration has fixed global rounds in the number of 25, 30 clients, 5 base stations, 1 global server. The nice thing is that the system is dynamic, and these drones in the simulation fly from one edge base station to the other one, so changing the clusters. The FedWG is the aggregation strategy, and we used Flower for the implementation. We can see in the picture here on the right that fixing the global rounds to 25, while we increase K2, so the number of rounds, we have an improvement in accuracy. At the same time, we reduce the number of epochs until a saturation point, which is around 90%. From this graph, we try to simulate also the energy consumption to compute the number of communication, and we can say that 5 epoch and 10 rounds, and 10 epoch and 5 rounds have the same accuracy, but the second configuration has much less energy consumed. We can say that the computation in terms of energy consumption is irrelevant. The number of communication is also reduced, but the time of computation is more or less the same. Then we set up a search problem with a partial search space, and we apply the Pareto front, and we try to maximize the accuracy while minimizing energy consumption, training time, and number of communication. According to our search space, we have K1 12, so 12 epoch and 5 rounds as the best score. At this point, we would like to compare our solution with the state of the art. And we can see from the picture here on the right that the standard federated learning is not very comparable with our solution because it's not able to reach our accuracy. While comparing with the only hierarchical federated learning present in the state of the art in the literature, they have to increase the number of rounds. So this means they will have much more energy consumed, much more communication. So this is not a good case for our drone scenarios. And these algorithms, the one in the state of the art, they are static. They don't take care of mobile devices. So there are no drones. They cannot move from one cluster to the other cluster, while our solution can do it. So we can say that our drone hierarchical federated learning application is good in terms of performance because we have low cost comparing with the state of the art. So going to conclusion, we can also say that this is really effective in terms of applying in complex scenarios where natural disaster management are involved. We're aware about a couple of limitations, because when we talk about training pictures, I mean, based on a data set of pictures in drones, a supervised learning is maybe not the best case, because we should label the pictures online. So this is very complex, because while the drone sample, somebody should label, and then the drone should train. So we are aware that this is a limitation, so we are looking for unsupervised learning approaches. And we would like also to test with use case algorithms, or based on fire detection or flood detection. So just to give some credits, this work is in collaboration with the Western Sydney University and the Swinburne University of Technology. The paper was discussed in UCC 2024 in December about the urgent computing and the management of cloud edge. We collaborate with the University of Utah and with INRIA. That's it. Thank you.
All right. Thanks a lot, Lorenzo. I think we should have time for a few questions. So yes, Jan is going to go through the room. You can start there. Yeah.
Thanks for.
It's on. It's on. Yeah.
Thanks very much for the interesting talk. So my question is about the security assumption, because this is totally different, to some extent, different setting than computers where you can kind of understand the attacks you apply to different devices. So in my opinion, you have got wider, or larger attack vector in that setting. So have you considered different attacks or subset of attacks that can be applied to your federated learning?
Yeah, not specifically in this work, but we are working also in security aspect of federated learnings, specifically in homomorphic encryption. We have some solution to encrypt also the communication of the weights during the federated learning process. And we are thinking also to make trustedness in the drones, because we can never be sure that one single mobile device, that in this case is a drone, is a trusted device that cannot modify the training or inject some poisoning attack or something like this. So we are thinking about it, and we can also discuss later the details.
Hello, thank you for the presentation. I would like to know, how did you evaluate the level of non-IDness on your system or your simulation? How did you evaluate it?
Is a pathological dataset. We used Flower dataset for the distribution of the classes.
Yeah.
All right. Thank you. I think we only have time for those questions.
Thank you.